Hello, Mr. Jones here, and we are starting a new chapter. For us, it's chapter 12, and it will be on equilibrium. And one interesting thing about this chapter is that we've already done a little bit of review. We did a little bit of the concepts in thermo when we did the not equation because we needed the Q expression. And where else did we see it? We saw it one other time recently. Trying to remember when that was, but I can't remember right now. But we have seen it a couple times, and basically what we reviewed is just the concept that equilibrium is the reactions going forwards and the reactions going in reverse, and they're happening at equal rates. So as an outside observer, if you were counting how much reactant and how much product you had, you wouldn't see any change. The amount of reactant and product is not changing. However, if you were to follow individual reactants and individual products, you might see one of them turn into the other thing, but at the same time, the reverse process is happening at the same rate. So we don't think of equilibrium as everything is stopped. We think of it as everything's still happening, but there's no overall change. And the other thing that we talked about was the idea of a Q and that Q, the reaction quotient, is the products over the reactants. And for some reason, my pen is huge. Okay, that's better. And it's the same idea as a K expression. A K expression is also products over reactants. They are mathematically the same thing. The difference is that this is at equilibrium. This is at some random place. It could be at equilibrium. It might not be at equilibrium. Who knows? It's just at some place. And this is going to be important so that we can actually compare these two things. This can be useful comparing these. Pins are not wanting to change their size. No, I don't want the rainbow pin. Okay. So up here I say what's in the numerator and denominator is always products over reactants. If you're at equilibrium, you can see I have a variety of different K versions. This top one here, Kc just means it's concentration, which would typically be molarity. Kp would be pressure, which you would use for gases. Ka would be acids, Kb would be bases, Kw would be for water. And yes, water gets its own equilibrium constant because it's so important, which we'll talk about that a lot more when we get to acids and bases. And Ksp stands for solubility product, and that has to do when you're making solutions. And it allows us to calculate where a solution will be saturated and things that will happen based on that. Over here, I'm saying this is important. We've already used it a few times before we even got to the official chapter. And now that we have it, we'll be using it a lot. All right, regarding the K value, because it's products over reactants, if a reaction has a large K value, and it doesn't matter whether it's Kc or any of these other Ks that I have over here, if it has a large value, that means you have a lot of product. And by large could mean that the K value is 10 to the third, or it could be something massive like 10 to the 7. Those are examples of large K values. If it has a small K value, that means that when you reach equilibrium, you don't have very much product. you have a lot of reactant instead. An example of a small K value would be something like 10 to the negative 3, or real extreme, 10 to the negative 60 or something like that. In other words, that means the reaction barely goes forwards at all. This would be something like if you take a rock and you put it in a bucket of water, a few ions might dissolve, but for the most part, the rock is not going to dissolve, so it has a very small constant saying that it's not wanting to go forwards much at all. Now, if you look at this next section here, I say direction of reaction. And you might be thinking, wait, I thought that reactions went forwards until they reach equilibrium, and then they're in equilibrium. Well, it's possible they could go backwards. For example, if you start with nothing but product. So let me just get a generic reaction. Let's say we do chemical A forming chemical B. If I start only with chemical A, let's put this at the fact that it's reversible. If I start only with A, it's got to go forwards until it reaches equilibrium. However, if I start only with B, it's got to go backwards until it reaches equilibrium. And then there's the complicated situation. What if we have both A and B? In other words, we have a handful of A, we have a handful of B, and we throw them in together. Well, we need a way to figure out which way is this going to go, or by random chance, is it already at equilibrium? So that's what this section's about. Instead of calling it K at equilibrium, we don't know, we're going to call it Q, the reaction quotient. We talked about this already earlier, but I'm just reviewing it. Just some picky things. You don't want to use brackets unless you know you're at equilibrium, so we'll use parentheses. And then what we'll do is we'll compare our Q value to the K value, and it will tell us which direction it's going. Right here, if Q is less than K, then the reaction will go forwards, and it will continue going forwards until it reaches equilibrium. If the Q is greater than K, then it will go in the reverse direction until it reaches equilibrium, and then that is pretty much the end of the story unless we make some sort of change. Now I have a mention here of the Q value and Le Chatelier's principle. And to remind you, Le Chatelier's principle is the concept that if you have something at equilibrium and you do something to it, if you stress it, the system will try to undo the stress and get back to equilibrium. But the point that this is making is that some stresses, like a change in concentration, that changes the Q value, and then it will react in a way to get back to equilibrium and the same K. But other stresses like temperature, the temperature actually changes the K value. And like it mentions, in either case, the species redistribute. That's a fancy way of saying it starts to react more aggressively in one direction until these become the same, which means you're at equilibrium. I want to talk about the fact that, notice I mentioned Kc so far. Kc, Kc, Kc. That just means concentration. So all these concepts apply to all the K values, but we're going to focus on concentration right now, just for simplicity. So take this first example. Fairly simple reaction. I have one reactant, one product. Double arrow. by the way, doesn't mean it's at equilibrium. That just means it can go in both directions. And we have the constant right here. Now, first of all, I have to point out there's a typo. It says if the initial concentration of N2O4 was 0.2 moles, moles is not a concentration. That's an amount. So please fix your notes. Anyway, it says the initial amount of N2O4 is 0.2 moles and the other chemical is 0.2 moles. They're both in a 4-liter flask. And we want to know what's the direction of the reaction. In other words, we've got a handful of reactant, a handful of product. We're going to throw them in a 4-liter flask. And I want to know, is one direction going to be faster than the other? Or by random chance, are we at equilibrium? There's a pretty low chance of that unless you do it on purpose. Well, in order to use the Kc value, and now is where we have to pay attention to that. Because it says Kc, that means we better be using concentration. And as I mentioned, moles is not a concentration, so I took the moles here, divided by the volume. That gives me the concentration of both chemicals because I had the same moles. So that's the molarity of N2O4 and also NO2. When you go to write your Q expression here, it's just like a K. Just call it Q because we don't know where we're at. Products over reactants. The product is NO2. Put the coefficient as an exponent and then N2O4. It has a coefficient of 1, so I'm just going to not write anything. Difference here is that this means we don't know where we're at. We don't know if it's at equilibrium or not. And then the brackets are replaced by parentheses because brackets technically mean you're at equilibrium. So I plugged in my numbers here and here. I still have the little squared. You do the math and you get 0.050. You compare this to the K that was given above, and notice the Q is smaller. And if you think about it, since Q is products over reactants, that means we have not made enough product yet to get to equilibrium. So this reaction goes forwards. So if I were to do a visual representation of this, I would say the reaction looks like this, in which it has a fast rate forwards and a slow rate in reverse. Over some period of time, what would happen is as we make more product and we consume reactant, the arrows would then change to something like this, in which the forward reaction is likely not going as fast and the reverse is sped up, but they're still not at equilibrium, and these arrows would keep slowly getting closer and closer until you eventually get this system where you're at equilibrium. And we could represent with that with equal areas. Another similar example here. Sulfur trioxide decomposes into oxygen and sulfur dioxide. So I've written the reaction here. Gives the Kc, 0.120. The reason the problem says assume the coefficients to be smallest whole number ratios is because if you write your reaction balancing it with different coefficients, it will affect your Q expression. So for example, if you did SO3 and then 1/2 O2 and 1 SO2, if you write the Q expression for this, you will get a different expression. So that's why the problem said do smallest whole numbers. In other words, it forces you to balance it like that so that we're consistent. So you might be thinking, well, what do we do if somebody does do this? Is that wrong? Well, it's not wrong, but there's something we'd have to do to fix our K value up here. And I'll show you that in the next lesson. For right now, let's just go with the way the problem said to do it. Determine the direction. So based on the reaction, here's my Q expression. Products over reactants. Coefficients become exponents, plugged in the numbers that were given. This time we get 0.63, comparing that to the Kc of 0.120. In this case, again, Q is products over reactants. Since this number is bigger, that means we have too much product. So this reaction is going to go in reverse until it gets back to equilibrium. And you would have the reverse of what I've shown with these arrows up here in green. It would be the opposite of that, in which the reverse arrow would be bigger than the forward arrow, and then they would slowly get the same until they are equal. Moving to the next page. All of a sudden, the notes get more clear for some reason. All right, solving for equilibrium concentration. So a common problem that you're given is you'll be told about a reaction, you'll be told something about concentrations, and you'll be asked, once this reaches equilibrium, what is the concentration of every chemical? Well, start by writing your K expression just to get it done. You're going to need it. Then do an ice chart. Again, when you do an ice chart, I stands for initial, C stands for change, E stands for equilibrium. We used these a couple of times earlier in cases where we weren't in equilibrium. In that case, E stood for the end of the reaction, but right now we're doing the classic version of ice chart where E is equilibrium. Plug in the X for the amount of something that's changing. And then you just fill out the chart, plug in the values into your K expression. And then I mentioned you might have to use the quadratic formula. Now, last year, if you ran into a problem where you needed the quadratic formula, that meant you were doing it wrong. This year, sometimes you just need it. Sorry. There are just times where there's no other way to deal with it but dealing with the quadratic formula. So you will see it pop up here and there. And I know you're going to love it. Now, I put a note here. First, feel free to put solids or even liquids in your ice chart. Now, you might say, oh, but I remember there was this saying where solids and liquids don't go in the equilibrium expression. And that's true. Solid and liquids don't go in the equilibrium expression. But you can still put them in the ice chart just so that you can keep track of things and it can be useful. So that's okay. Next, in the ice chart, you can use moles, molarity, atmospheres, but never grams. You can never use grams in an ice chart because an ice chart is based on stoichiometry and a balanced reaction. And you can't use grams because things have different molar masses. The thing you can always use in an ice chart is moles. That's a certainty. Molarity you can use if the volumes are not changing. And atmospheres you can use if a few different things aren't changing, like volume and temperature and pretty much that should do it. So you might see a problem where you get to use different things in the ice chart. But of course, if you're ever not certain what to use, moles is the one to go with. All right, take a look at this example. Interesting reaction in that all the coefficients are ones. So 1 CO2, 1 H2, 1 CO, 1 H2O. First thing you should do is write the Kc expression. Again, C just means concentration. That'll make more sense once we start looking at other versions of K. Products over reactants, and everything has a coefficient of 1, so all the exponents are 1. Next, do your ice chart. Now notice I lined my ice chart up underneath the reaction. if you don't do that, you'll have to write the reaction again, and I was just saving myself some time. So I lined it up so that my CO2 lines up here, my H2 lines up here, my CO lines up here, and my H2O lines up here. Initial, you're typically told this. This is kind of just random and made up. And so in this case, it says the carbon monoxide is right here, 0.1. Water vapor is 0.1. They didn't talk about reactants at all. So I like to put a slash just to say that that doesn't even exist. It just emphasizes that to me. And then calculate the concentration of each gas at equilibrium. Well, since I only have product right now, this reaction has to go in reverse. So I don't need to bother with that calculation that I showed you earlier, calculating Q in this case, because it's obvious that this reaction is going to go in reverse until it reaches equilibrium. So I plugged in plus in my reactant side changing because the amount of reactant has to go up. I put in negatives on my product because product has to go down. And then you just fill out each column. So nothing plus X is X, nothing plus X is X, 0.1 minus X is 0.1 minus X twice. I don't have the answers yet, so don't look at the box yet. Plug these values into the K expression, which I did here. So those are the numbers. I've also included the KC that I knew from up here. Now at this point, there's a mathematical tool you can use to avoid the quadratic formula. In this case, we have perfect squares because I have a square on top and a square on the bottom. And in this case, just take the square root of the entire stinking thing, at which point the square root of 0.64 is 0.8. And the square root of the other side just gets rid of the square. And this is a much better mathematical situation to deal with. I cross multiplied, isolated my X, and finally got an X of 0.0556. You then take this and you plug it into your equilibrium row, and that gives me 0.0556 for both reactants, and my products have gone from 0.1 to 0.044. And you can do a little bit of a sanity check. That makes sense. My products went down, my reactants went up, and that's what it had to be. All right, next one. Let's go ahead and just look at the whole thing here. One reactant, N2O4, one product, NO2. We saw this situation on an earlier one on the other page. Kc is given. In this case, they only gave us N2O4. So we know automatically, since they only gave us reactant, this reaction has to go forward. So you might be thinking, wait, on the other page, we learned this technique of comparing Q versus K. The only time you have to do this is if you're given both reactant and product. But these last two examples, we were only given product in the first, and we were only given reactant here. So you don't need to bother going through all this stuff. It just would waste your time. Anyway, here's my Kc expression. Started my ice chart. Initial amount of reactant is here. There is no product, so put a slash or whatever you want to put. For the change, it's nice to make, excuse me, one of them a 1x and then let other things become higher numbers of x. So in this case, since it's 1 to 2, I chose to put my x here, and it's negative because reactants are being consumed. And then that, because of stoichiometry, whatever N2O4 does, because of the invisible 1, the NO2 does double. So I get a plus 2x. Add your columns. That gives you 0.1 minus x, 2x, plug that into your equilibrium expression along with the equilibrium value. In this case, after you can't do perfect squares, and after you do your math, you end up with this scenario. And when you see this scenario, you should notice that it equal to 0, at which point, if you can factor it, go for it. If you can't, label A, B, and C, go to the quadratic formula, enjoy. You'll get two answers. You'll get a 0.060 and a negative 0.15. And what you need to do at this point is try both of them back in our ice chart right here and see which one makes sense. If you plug in a negative 0.15, you will get a negative amount of reactant and negative amount of product. That doesn't make any sense, so we can't use that one. If you plug in 0.060, you get that the reactant went down from 0.1 to 0.04. The product went from nothing to 0.12. That does make sense, and thus that must be the correct answer. And that actually takes care of this lesson.